This is a really big idea that I found in a textbook, and I just copied it over. I don't know if this is in our textbook or a different physics book, but it's interesting that the implications of science and physics, how they can sometimes intersect with philosophy. And what I think is interesting is for thousands of years, people believe, you can read this if you want, basically for thousands of years, people believe that there was different physical laws that govern the heavenly bodies and the earthly bodies. And what Isaac Newton figured out when he figured out this universal law of gravity is that, in fact, the physics of our planet is exactly the same as the physics of all planets, basically, in our galaxy and also our universe. So it basically made this heavenly bodies, I guess, a little less mysterious and sort of unified, these different theories that people had. And later scientists also unified like electricity and magnetism, and this led the scientific community to, in a sense, want to unify everything into one grand unified theory. That's kind of, you'll notice from the scientific community, the goal of physicists and theoretical physicists to find one unified theory like string theory that ultimately explains everything about the natural laws. So it's interesting. Give this a read if you're interested. But here's the universal law of gravity right here. It's on our formula sheet. It's probably the most important formula we're going to have all year long besides Newton's second law. Really important. It's also a very weak force, as you can tell. This constant out front here, this G, it's not very big. So, this force is very weak. It's so weak, in fact, that we can't really feel the gravity between us, or we can't feel the gravity between, us and almost any other object on Earth. We can feel the gravity between us and Earth itself. But that's about it, because Earth's so big. It has such a big mass in the numerator of this equation that we can then, sort of feel that force. But keep in mind, it's also an inverse square law, so it does get weaker as you go away from the center, which we'll talk about. It has all kinds of interesting consequences that we could talk about for days, which we will talk about. For example, the moon falling around the Earth, or the speed required to send something into orbit. For example, the curvature of the Earth is about, for every 8 kilometers, the Earth falls away about 5 meters, which is interesting because 5 meters is what it takes an object 1 second to fall 5 meters on average, because we have 10 meters per second squared for gravity. So in 1 second, then, that means that if you launch something at 8,000 meters per second, or 8 kilometers per second, it would exactly match the curvature of the Earth, and it would be in orbit. So if you could launch something with that kind of speed, it would just continually fall around the Earth. And that's exactly what speed you want a satellite to go in order to fall around the Earth. Now, if you launch it faster than that, what's interesting is, it'll actually be in orbit. So if this is Earth, and you launch something faster, it's going to be more of an elliptical orbit. If you launch something even faster, it can fall out and be a hyperbola, a hyperbolic path, and escape orbit. But all kinds of consequences. We could talk about the ocean tides. Obviously it had to do with the moon pulling on the water on the Earth and elongating the water here closest to the moon, and actually away from the moon as well. And then you have low tides on the sides here. And if the sun is also in line, the sun has an impact on the tides as well, not as much because it's so far away, but it does. So if the sun and the moon are aligned, then you get a bigger tide here. There's a word for that. I can't remember if it's neap tide or something, or spring tide. I can't remember. But there's also, and then if the sun is at perpendicular, then it kind of cancels out a little bit of the moon. Your tides aren't as dramatic. But basically, because water is a liquid, and the moon does pull on it, and so does the sun, you can see the stretching of the water. The water will essentially, morph because of that force. And so there's all kinds of implications for gravity. We can talk on and on about gravity, and we will, as we talk about astronomy and watch Cosmos and other things like that. Another one is black holes. We'll talk about black holes, which are fascinating, actually exist. You can see them with radiation cameras. You can see black holes emitting quasars, which are awesome. And there's some at the center of our galaxy. So all kinds of implications for gravity. Also, check out page 177 of our textbook, with this experiment, scientists were able to weigh the Earth way back in 1798, which is pretty impressive. And it's just using Newton's law, now that it's known. You know, if you have the force, you can measure the force between these two things. And if you have one of the masses, then you can figure out the other mass, which is the mass of the Earth in this case, which is pretty cool. All right, here's a better picture of Newton envisioned this satellite motion that I drew for you a second ago. You know, if you launch a cannonball slow enough, it'll just fall to Earth. If you launch it faster, it'll go further. But if you launch it at the exact right speed, it'll just continue to fall around the Earth until it hits the cannon in the back. So that's how he first envisioned satellite motion. The period of a planet orbiting the sun formula is right here. It's on our formula sheet. Obviously, R stands for the average distance that we are away from that object. G is the gravitational constant, and M is the mass of the sun. And these values for R, the average orbital radius values, they're on page 173 of our book. I will give that to you on a test if I asked you to use this at all. So if we're going to use the universal law of gravity, we can do some combination of some formulas to get another formula, which is on our formula sheet for the speed of a satellite orbiting the Earth. G is once again the gravitational constant, M is mass of the Earth, and R is the distance we are away from the center. Now this works for not just the Earth, but we could use the mass of the sun. We could talk about the speed of a satellite orbiting the sun, or any other object for that matter. We just swap out the mass of the Earth for the mass of that object. Here's another formula for period of a satellite orbiting the Earth or orbiting anything else. Like I said, same thing. You swap out mass of the Earth for what object you're talking about, and you can use this to talk about how long it takes for a satellite to orbit the sun or any other object for that matter. It's a useful relationship. It's on our formula sheet. All right, so here's an example problem then. It says assume a satellite orbits the Earth, and the distance that we are is 225 kilometers, but that's above the surface. And we need to keep in mind, we need to think about being in meters, and we also have to add on the radius of the Earth here. But we're given that the mass of the Earth is 5.97 times 10 to the 24 kilograms, and the radius of the Earth, they give us 6.38 times 10 to the 6th meters. What's the satellite's orbital speed and period? So orbital speed, the formula that we had for that is the square root of G, the mass of the sun, which we'll use mass of the Earth here because we're orbiting the Earth, divided by R. And then the period formula I gave you a second ago was 2 pi times the square root of the average orbital radius cubed divided by G times the mass of, in this case, the Earth, not the sun. So we're going to use these. And once again, when we find R, this distance, this average orbital radius, we have to add this right here, which we're going to call that 225,000 meters, and add it on top of the other one in order to get the actual orbital radius that we're going to use, which is about 6605000, so about 6,605,000 meters. That's going to be what we use for R, both here and here. And the mass of the Earth obviously goes in for mass of the Earth. And G is our gravitational constant, 6.67 times 10 to the negative 11. That's off our formula sheet. And that goes in for capital G here. So if you solve both of these just by substitution, for velocity you should get 7,764, about 0.5 meters per second. And then for the period, if you plug in here, you should get 5,344.9 seconds. And this number seems a bit small, but seems like that's moving pretty fast, but we'll double check that in class. Okay, gravitational fields then is a place where another object experiences a force due to the interactions between its mass and the gravitational field. So here's a nice diagram of a gravitational field. We'll talk about magnetic fields as well that are going to be very similar. But you'll notice these arrows are closer together, closer here, and then the arrows get kind of further apart outside here, which is like kind of like you want to look at a cross-sectional area, how many arrows go through that cross-sectional area. You know, if you compare that to out here, you'll notice that the field is just stronger in here. That's one way to look at it visually. And then, you know, mathematically, we're going to do this with electric charges as well around electric fields. But we could take like a test charge or test mass in this case, and we could place it in here. We could draw a free body diagram and find out there's only one force on it, and that force is gravity. So we can say that's ma, or that's the universal law of gravity, set those equal. And what we find is that this is going to be m1 then, and the mass of the Earth will be m2, which I'll say mass of the Earth, over r squared. These m1s cancel, and we get this equation for gravitational field strength, which is basically the same as our acceleration due to gravity. On Earth's surface, that's 9.8, and then obviously in space, then the further you get away from Earth, the weaker gravity gets. In space, it's a little less than that, about 8.7. Okay, let's spend some time now talking about Einstein's theory of gravity, because obviously, you know, Einstein improved on Newton's theory of gravity and figured out a heck of a lot more, which isn't technically part of our curriculum, but it's so fascinating. There's no reason that we shouldn't talk about it for a while. So let's read this in our 225 book, page 184, and let's also look at the space-time fabric that Einstein talked about. A great video for that is this gravity visualized video that you can find on YouTube. It's fascinating. It'll blow your mind, hopefully. So let's take the time out to do that. And then the homework is right here, so we can practice some of these problems. Hopefully this helps.